Whether you're a programmer or a malware analyst, learning to reverse engineer is an essential skill that teaches you what's really going on in a program. In this video, I'm going to break down my 5 levels of reverse engineering, starting with level 1, strings. When we're doing reverse engineering, typically we have a question we want to answer, something about a program we want to figure out what exactly is going on. The name of this program is just a long hash, but we do know it's a piece of malware. It came from an online malware market, and we know that it has malicious features, but we don't know exactly what they are. Inside of a binary, typically we have a bunch of gobbledygook, a bunch of nonsense content that represents the program as it was created by the assembler, but you will see some of the information in that binary is actually human readable. When the human writes the program, some of the human content, the strings, get left inside of the program, and a lot of the strings can kind of reveal what's going on the inside. To get a better view of the strings in our program, we can simply use the Linux utility strings. And I like to use strings with a length of 10. Those longer strings typically give us a better insight into what's actually happening in the program. And we can use that on our program here. This long hash string will pipe that into less. This gives us all the strings that the binary could find, ASCII printable human text that can kind of explain maybe what the underlying functionality of the program is here. We have the contents of an HTTP post request, and we have the authorization field, as well as a bunch of other interesting fields to make it look like maybe the content's coming from a Firefox or an Opera browser. Now, when we're doing reverse engineering, we have a fundamental reverse engineering question. What does this program do? And if you have any experience in the world of RE, you may very quickly see what is happening here. This malware is exploiting a command injection vulnerability inside of some Huawei device that is vulnerable on what looks like it's SOAP or likely SSDP protocol. What we can see here is that it is calling the bin busybox program to this IP address 118.172.110.214. And it's using that IP address to call down some binary and write it as /mips. Just through looking at strings alone, we can see very quickly that this piece of malware is exploiting a vulnerability, and we also can see the IP address being called out, 185.172.110.214. When a person writes code, at the end of the day, error codes, maybe names of source files, certain metadata is left behind in the program. And we, as reverse engineers, can go look at those strings and kind of infer what did the human mean to do when they wrote this program. Now, obviously, we have some error codes here that tell us what the program could do, but the most obvious string conveniently at the top shows us, oh, this is a piece of malware that exploits a command injection, and it downloads malware likely for a Huawei device, either maybe a Huawei router or a Huawei hotspots and something like that. Yeah, it kind of sums it up here, right? Huawei Home Gateway. It kind of shows very easily what we're working on here. So while strings may not get you everything, they get you a lot of what you need, but what we can do is level up to the next level, static analysis. Static analysis is the art of taking that program where you have questions about it and looking at the code, going deep into the binary and reading the assembly and the pseudo-C to figure out what exactly does the program do, or what does it say that it should do. Here we have a program called Crack. I know, very generic program here. Crack is a Crack Me, a very fun kind of Sudoku-esque puzzle in the world of reverse engineering. Literally, it's just a program that we're going to type the command to run the program, and it's going to say, hey, can you enter the right password? And I'm going to say, is it password? And it's going to say bad kitty. Okay, I didn't make the program, just letting you know. I found this online. I apologize for any weirdness and what you may encounter here. Okay. So what we know is that there is a prompt in the program that says enter the right password. We try to put in a password and it says bad kitty. So what we have to do is statically analyze the program and figure out what is the right password to make it say, I'm assuming good kitty. Okay. Yeah, so we can apply the lessons from the previous example, right? We can do strings on Crack, and this is actually what I suggest for doing basically any reverse engineering task, right? If you look at the strings here, I'll kind of pump this into less to get a better view of it. You do see some very important information. You're able to see what functions a binary imports, as well as maybe some other symbol information to tell you what the program does. So here we see puts, a printing function, read, a function that reads from the user, and then write, a function that writes to the user. We also can see this program was compiled with glibc version 2.3.4, and we do also see that good kitty string. Okay, so I was not crazy, there is a good kitty. So, again, this is kind of where strings ends. This is where strings stops getting us information, and now we want to enter the level of static disassembly or static analysis. To do static analysis, we want to use a program that allows us to view the code and to view the assembly of the program to kind of take it apart and figure out exactly what the machine instructions are. What did the CPU get told exactly what to do? We can start by using a tool called object dump, and we're going to object dump this program to dump all the assembly instructions. This is the raw code that the program gets told to run. Now, this is not very human readable, but we could sit here and walk through every instruction byte by byte and use this to take apart the information required to find that password. So what we have here in the object dump view is the assembly instructions, the individual opcodes the CPU is told to execute to make the human intent of our program happen. When we originally write code, typically we write code in a language like this. This is C code, where we create a allocation for a buffer, we read data into a buffer, and then we print the buffer, right? We are able to express the intent of our program through the syntax of the language we're using, like C, for example. At the end of the day, though, the computer doesn't care about our human intent, the names of functions, the names of variables. It just cares about what instructions do I take. And so when we compile the program from a language like C down to a binary that can be ran, we're left with only this information. Reverse engineering is the act of taking these instructions and trying to infer the human intent. What do we think the C code looks like through the output of these instructions? Now, this view of the disassembly is not very pretty. Luckily, programs like IDA give us a very clean graph view of all the blocks in the program. It's a lot of words I just said there. Let me break down what I'm talking about. So if I open the program in IDA, what we have here is the blocks of the code. A code block is a piece of code that will run to completion no matter what if the CPU begins to run execution there. Well, you'll notice we have certain branches that the blocks can take that conditionally execute based on the results of our instructions. So for example, right here we have a jump below or equal to label that jumps to another block if the previous comparison between the A register and 19 are the same. Now, I know I just said a lot of words there, very confusing stuff. This process of reading the assembly and figuring out what branch is taken based on what the program does is the art of static analysis. Now, luckily, people like the team at Hexrays who write IDA and also the team at the NSA that made Ghidra have spent years of work creating these things called lifters that lift this very difficult to read assembly up to a pseudo C, a representation that looks like what C would have been by the author of the program. So we can open the same program in Ghidra. This gives us the best guess of what the code would have looked like if written by the author in C. Obviously, we don't have the real C, but Ghidra took a good guess at what the assembly looks like and then said, hey, this block looks like this in C. This block looks like this in C, and did that over and over and over again until eventually we got this representation of the code in C. Obviously a little messy, but much better than having to hand churn through all of these assembly instructions. So if we go and look at the code, we're kind of looking for this reality anchor, right? We know we're gonna print bad kitty or print good kitty. Okay, so by printing bad kitty, this happens when this local BD variable is equal to 0. So let's say that the local BD variable, instead of local BD, it's now called is correct. Okay, maybe that's a bool that says is the flag right or is the flag wrong. And by doing this analysis, we're kind of using this information and we're reverse engineering based on the behavior we're observing statically. What should the program do and what was the human's intent when they wrote the code? So what we notice is the only time that is correct is written to, is modified, is at the beginning of the program. Here we have is correct equals 1. And it does some kind of for loop and it checks over our math and then says, okay, we're going to iterate and do while 7 is less than local BC. Okay, maybe this is going to be flag length, for example. And it's going to look inside of some index, some array. Oh, okay, so this is the buffer that gets read from the user, right? We see we have the read operation here. The read operation reads from 0, standard in, and it reads to this buffer. So this buffer we can say is user input. So if we say if user input of flag length, no, let's call this counter actually, because it's not going to be flag length every time. It's going to read the index into that string, and it starts at 0. So if user input of counter is not equal to local B8 plus counter, then is correct to 0. Okay, so what this implies is that this local B8 buffer likely has our flag. This local B8 is being used to compare against our information. We can change this probably to a character pointer. Change that to a character array, and we can also recall it. We can rename it the flag variable. So flag int of counter. So now we can go back and figure out, okay, how is this variable set? And we can see basically when the program starts, it does a lot of math operations. It does this Puler3 thing, which is another function with some math in it. And so we know now through static analysis that the value that is set in this part of the code is going to be the flag that is checked in this part of the code. So we need to make our input equal that output. Now there's two ways we could do this. We can spend more time statically analyzing the math operation here and then do the factorial operation here and do a lot of kind of hand jammy math. Or we can move on to the next part of this video, level 3, dynamic analysis. Dynamic analysis is the art of watching the program run live and observe it do its functionality in real time. We're not going to spend any time guessing based on static analysis what it does. We're literally going to watch it perform its actions. The reason we want to do dynamic analysis here is we know for a fact that at this point in the code, there will be a variable that has the flag, the input that we need to put into the program. Now we could spend time going through the program and statically figuring out the exact mathematical operations, or we could just let the program do the math for us and catch it in the act and look at it dynamically. The program we're going to use for dynamic analysis is this program called GDB, or the GNU debugger. What the GNU debugger or GDB lets us do is run programs and then set these things called breakpoints, an instruction that tells the CPU, hey, stop what you're doing, I have questions to ask you. So we can run the program in GDB, and I have GEF, the GDB Enhanced Features framework that makes basically GDB prettier, it prints more stuff. And we can do R to run our program. Now what you'll notice here is that the program behaves the exact same way that it's supposed to behave, and we type in the password, and we type in the wrong password, and we get the same functionality. The reason for this is we didn't put in any breakpoints, right? We didn't tell the program, hey, can you stop at this location? The most important question to ask is, where should I stop and observe the program state? For me, I kind of want to stop right here at this counter location to figure out, where is this flag buffer, and can I just look at it, right? Is there a location on the stack that already has the flag, and can I just use that to check against my own input, right? So what I'll do here is I'll stop right before the loop starts, which will be at this instruction here. What we can do is set a breakpoint at main and run our program and then do vmmap. This will show us exactly what location the program is getting loaded to. Now, because there is a position-independent executable, typically ASLR, the randomization of address space, would affect this, but because we are in GDB, GDB temporarily disables ASLR. So we know that by default, the base of our binary is always at this address. Now what we can do is some quick math to basically say, okay, if the position-independent executable starts at this address here, let me pull it up, at hex, 100,000, and I want to stop at 100,001.45C or 4C5, we can do a quick little public math and set a breakpoint at this location, and that will stop the program right before the loop starts. The reason I want to stop at right before the loop starts is because in theory, our flag is just a location on the stack. So if I print all the stack variables while the program is running, I should just see the flags. Let's do that right now. Let's do run. We hit our first breakpoint in main that I set. We'll do continue to keep going. Enter the right password. This could be literally anything. And now we've broken at that assembly instruction that sets the counter equal to 0. So then to view the contents of the stack, which could potentially in theory contain the password here, I want to do context stack. And this will show me the top of the stack down to the bottom of the stack for the stack frame. And what you may immediately see is this suspicious string that is, 1, 2, 3, 4, 5, 6, 7, 8 characters long. If you remember from our program here, we saw that the loop was making sure that the counter was not greater than 7, right? So if we have an 8-character string, it's on the stack around the place that it should be. We've observed it dynamically be created, and its length aligns with the contents of this loop. It might just be the password. So let's give it a shot. Crack me here. Good kitty. Sorry about that. Anyway, sometimes programs are too hard for static or dynamic analysis. So this moves on to the next level of RE, symbolic execution. Symbolic execution is this amazing concept in reverse engineering where we effectively turn a program into a math problem and then use a satisfiability solver to see if a program execution can or cannot happen. Let me explain what that means. So here we have this example piece of code called check value, right? And we have int x. If x is greater than 10, return greater, but if x is less than or equal to 10, we return less than or equal to. What a symbolic execution engine will do is turn this function into a graph where the input is symbolic. What we can do is tell the graph, what are the conditions of X required to go down this branch of the graph? And it will use the underlying satisfiability solver to come up with the answer to that question. It'll say, oh, we've done the math on your program, and to get to this branch, X must be less than or equal to 10. Now, we can actually apply this to programs that are much more complicated than just simple value checkers. We actually can take basically any program and turn the totality of that program into a math problem and use that to figure out, how do I get to block X while avoiding block Y? Very good for reverse engineering. Now, to do symbolic execution, we're going to use a library called Anger. Now, Anger is a Python library that is an open source binary analysis platform. It allows us to take programs, view the graph of the program, and specify, hey, can we go down this path? Can we go down this path? Can we avoid this block? And then turn those sets of constraints, as well as the constraints of our input, into a math problem for Anger to solve. And by doing this, we can figure out how to make the program execute specific tasks without having to manually do total static reverse engineering. So the program here is this file called engine. Engine is yet again another crack me. We had to figure out the input to this program to figure out how to get the flag to come out, or maybe the input itself is the flag. We can run the program engine and it says, welcome, we're doing things a little differently around here. You're going to tell me a tidbit about trains. Are you ready? And I don't know a ton about trains. So let's say trains are cool, maybe, question mark. And it says, nope, I guess you're not a total trainiac. Come give me your best tidbit. I guess you don't know a lot about trains. Okay, so we now know that the input to this program has to be such that we give them a cool train fact, I guess, and that makes the flag come out, or that fact is the flag by itself. We can open this program in Ghidra, and we'll see here pretty quickly that we have kind of these two main branches we can take that really tell us, like, did we get the program right, or did we get the program wrong? So I guess you don't know anything about trains is a branch we just experienced. Otherwise, chugga chugga choo choo, you're the little engine that can. Congratulations, you passed the program. And the result that makes this occur is inside of this 101640 function. I did some static reverse engineering, right? I went deep on the program in the C view here, and this is a very complex program. I could spend a lot of time here and figure out exactly what is happening and kind of manually reverse engineer the content required to make the flag come out. But we also can give symbolic execution a shot. I mean, this is a pretty simple program from the outside. It doesn't seem to import a lot of libraries, which are a big concern for reverse engineering with symbolic execution, right? If there's a lot of I/O, you have to stub out that I/O. The one issue you run into with symbolic execution is this idea called path explosion, right? If the number of potential states your program can be in can be a very large value, if it's a very complex program, that means that we're going to literally exhaust either the RAM in our computer or CPU time to calculate the answer to our problem, and that isn't a good thing, right? So what we can do is do reverse engineering to figure out, how do we constrain the graph to make it so that the symbolic executor doesn't run out of memory, right? Or doesn't create too many states to solve for. And so this is the script used to solve this challenge. What we're going to do is create an Anger project and open the program. The program is called engine, right? We're going to tell the program to automatically load and execute the initialization of libraries. We're going to create this thing called a BVS, or a bit vector symbolic. A symbolic variable, the root of symbolic execution, is a variable that does not have a concrete value. It is going to be a value that is solved mathematically by the underlying SMT solver, the satisfiability solver. And then what we're going to do is we're going to concat all of those characters together into this longer symbolic array. We're going to fully initialize the state of the program with the options given up above. And we're going to say, hey, the input to this binary is going to be a symbolic array. We're going to pass in a completely fake, not yet solved block of information. What that will allow Anger to do is create the states, and in those states where standard in gets used, it fills them with symbolic values that will later be solved by the math engine. Now, what we're going to do is take that state we made, the full init state, and we're going to add constraints to the flag. Again, when we go to actually solve this problem, we could potentially have path explosion, where we can literally permutate the state of the program into every possible combination of inputs. So by adding constraints where the given input is ASCII printable, and the way you do that is by saying if it's greater than hex 20 and less than 7F per character, that takes the number of states down by almost over half, right? So it drastically reduces the amount of work required to be done by the symbolic executor and making the overall runtime of this program very, very small. Now we're going to run the program symbolically, and we're going to take every state that has the word chugga in it and append that to our list of good states, right? So in the background, what it did is it ran the program and used our constraints and filled in standard in with these symbolic values. We found all of the states that were generated that had chugga in them. And why did we say chugga? Because chugga is a string that is in the good state, right? We have, again, two possible end states we can get into. When the program ends, we either don't know anything about trains or the word chugga is in the output. So by retaining only the states that have chugga in them, we now know, okay, cool, this is a good state that could symbolically have the flag. Now by taking that state that has a you did it output, we can print the standard input for that state, and that will contain the input that got us there, which could potentially be the flag. Let's see. Now running these kinds of programs do take on the order of minutes to sometimes hours, so we'll let it run in the background, and I'll see you when the flag comes out. We'll see you there. And there you go. So that's our flag there, using symbolic execution to solve the program pretty much automatically for us. I want to highlight that symbolic execution, while powerful, doesn't apply to every scenario. Not everything can just be symbolically executed. Mathematically, it's very difficult to do this. And like from a computation standpoint, it's very easy for the states provided to Anger to path explode and use your resources completely or be mathematically unsatisfiable. You need to give it a set of equations that it can solve. If you say x plus 1 equals 3 and you then say x equals 10, well, that's not a real, you can't solve that equation. We can wrap this all up by going to level 5, finding real bugs in real software. Level 5 is taking apart real devices in real life and finding vulnerabilities through reverse engineering the software of these devices. I got this weird device off Temu. The whole content of how I got this thing, how I did this process, and what I found is in a separate upcoming video. But I want to kind of talk about how this works and what you can do to take this approach in finding bugs yourself. So I was able to extract the firmware off this device through a weird method that I'll talk about in another video. But basically, I was left with this file called full.bin. If you do a little strings analysis on full.bin like we had been before, you kind of get a bunch of weird stuff. But you'll see there's a bootloader here and a bunch of file system information, like we do /var, we'll search for that, or /bin maybe. Yep, bin ash, right? So we can see that there's metadata related to potentially a file system or something like that in this file, right? So we can use this program called binwalk to recursively find objects and either decompress them or extract them, and use that to expose potentially a file system inside this weird firmware file. If we do binwalk me on full.bin, M is matryoshka, or like the Russian nesting dolls, right? It basically recursively goes deeper and deeper and deeper into files that it finds, and E for extract mode. We can eventually get it to expose in the full bin extracted file a bunch of little other files, right? And so because this is an embedded device, typically there's going to be like a bootloader on here, maybe a stage 0 bootloader, and then finally the full loader that loads the kernel and then the file system. And so that file system we're talking about is this squash fs root. By typing ls in here, bada bing, bada boom, we see kind of the root of an entire Linux distro. Very cool stuff. Where we typically start with these, if you go to the etc folder and see if there's any files that tell us kind of how the device kicks off. Typically in the rcd folder, we'll see all of these startup files. This kind of tells us in what order and at what privilege level the part of the device kicks on. The GPIO switch, then Dropbear, the SSH server, and then maybe the cron jobs, then ComuOS. This is what gets a little interesting, right? So if I cat this starts the primary service that hosts the HTTP server. So what this device actually is basically a Wi-Fi router, Wi-Fi repeater. And again, I got it for like $5 off Temu. But what we can do now is use the previous tools that we've learned, like dynamic and static analysis, and crack open user sbin ComuOS into Ghidra and go figure out how it works. Find where there may be misuses of user data and potentially vulnerabilities in software. And by cracking open these binaries in Ghidra, we can then use our previous levels like static analysis and strings analysis to figure out exactly what's going on inside of this binary. What we found here is a table of strings that are correlated to a function. So maybe there is like an opcode parameter in a query or something else like that, that when you give it rtime info, for example, it calls this function here. We now know that maybe there's some amount of data the user controls, like parameters like UDP connect, TCP connect, and if there's a vulnerability like a stir copy that's too big or something similar, we may have found a 0-day in a device, which is a video topic for another day. Anyway, guys, I hope you enjoyed this video. If you did, go check out that video about this device. It's pretty cool. And if it's not out yet, go check out this video while you wait. I hope you guys liked this video. If you like these kinds of videos, let me know in the comments, and we'll see you in the next one. Take care.